In a PNP transistor with no external voltage applied, the concentration graphs of majority and minority carriers in the neutral parts of the P and N regions are horizontal. No current flows in the external circuit. The forward voltage applied to the emitter base junction, together with the reverse voltage applied to the collector base junction, cause a large current to flow in the collector circuit and a very small current to flow in the base circuit. We will now consider the concentration curves of the minority carriers plotted in a linear graph. With no voltages applied, the concentration curves are horizontal. But when voltages are applied to both the emitter base junction and the collector base junction, the concentration curve in the base region will be at an angle to the horizontal axis. The base current, or input current, is proportional to the difference between the surface area of the indicated triangle and that of the original rectangle. This difference is, in fact, a measure of the number of additional recombinations per second. The collector current, or output current, is a function of the angle formed by the concentration curve of holes in the base. If, in addition to the forward bias, we apply a stepped voltage pulse to the emitter base circuit, we can examine the variations in the collector current as a function of time. At this stage, the collector current has a certain low value. But when the pulse is applied, the collector current reaches a higher value. What happens to the collector current when this pulse is applied? This sharp rise occurring at the leading edge of the applied voltage pulse causes the emitter base barrier region to become narrower. Simultaneously, the number of holes in the base near the barrier increases. Consequently, the whole current flowing from the emitter into the base will be temporarily higher, causing the concentration curve to straighten again. The variations in the angle of this concentration curve near the collector base junction are directly related to the variations in the collector current. The time taken for this current to attain its new constant value is called the rise time, TR. When the pulse is cut off, the current decreases. What happened at this trailing edge of the pulse? The width of the emitter base barrier region increased, and the concentration of the holes near the junction followed this change immediately, after which the concentration curve straightened out again. Thus, the changes in the angle of the concentration curve near the collector base junction are directly related to the variations of the collector current. The time taken for this current to fall to its original value is called the fall time, TF. So far, we have studied the effect resulting from the direct application of a stepped voltage pulse. This technique, known as voltage steering, may, however, lead to very high input currents. In practical circuits, therefore, this input current will always be limited by an input resistor. Because of this limitation on the value of the input current, it is said that the transistor is current controlled. Consequently, there will be a considerable increase in the times necessary to bring about a change in the concentration curves of holes and electrons in the base. Thus, TR and TF will also increase. Up to now, we have considered the time taken for small current variations to occur, which in fact means that the transistor is acting as a pulse amplifier. When a higher input voltage is applied, the output current also becomes higher, but the rise and fall times remain the same as before. Let us now examine the possibilities of using a transistor as a switching element, with input and output resistors. But, first of all, let us refer to a series of typical output characteristics with load line and working point. Again, if we apply a small variable voltage, the variations of the input current, IB, will follow exactly the variations of the input voltage. But the variation in the output current, IC, will not be the same. In this example, the time taken for these current variations to occur will be rather long compared with the pulse duration. If we now apply a much higher input current, the collector current will be limited by the saturation value, minus ICS. So TR will now be much shorter. This effect can also be explained from the concentration curves. Consider first that the transistor is working in the normal state. As soon as this stepped voltage pulse is applied, the transistor will continue to operate in the normal state, and the collector current will increase as a function of the angle formed by the whole concentration curve. But because this current flows through the output resistor, the voltage drop over this resistor increases, and consequently the voltage drop over the collector base junction decreases to such an extent that this junction becomes biased in the forward direction. The transistor is then saturated, and the collector current remains constant. The whole concentration curve rises still further until the number of recombinations per second becomes equal to the base current, which is, of course, the input current. If, however, the transistor had not reached this saturation state, the collector current would have attained a much higher value. So in order to reduce the time taken for the current to become stable, it is necessary that the transistor be brought rapidly into saturation. In the same way, we can expect that TF can be reduced by bringing the transistor rapidly into cutoff. To obtain an overall picture of the switching action, we must start with the transistor biased at cutoff, and then apply a very high positive stepped voltage pulse. The total input voltage, VI, shown as a function of time, will now be of this form. Initially, because the transistor is at cutoff, the collector current is 0. Both junctions are reverse biased, and therefore the whole concentration curve is horizontal and of a very low value. What happens then when this high stepped voltage pulse is applied? The application of the pulse sets up an input current, but the electrons entering the base do not disappear due to recombination, because the concentration of holes in the base is still very low. Therefore, the electrons in the base and the holes in the emitter, which contribute to the input current, are absorbed in creating a narrower emitter-base barrier region. This continues until such time as the barrier becomes biased in the forward direction, after which the holes start to flow into the base. The time taken for this space charge region to become neutralized is called the turn-on delay time, TD. From then on, the emitter-base junction is biased in the forward direction, and the concentration curve starts to rise, and with it, the collector current. Part of this current is consumed in reducing the width of the collector base barrier region. This action continues until the collector base junction is biased in the forward direction. The concentration curve continues to rise, but the collector current remains at a fixed value. Now let us see what happens when the transistor is again switched from saturation to cutoff. The electrons are drawn out of the base and the surplus holes quickly disperse. The level of the concentration curve drops to a point where the collector base junction again becomes biased in the reverse direction. However, as the angle has remained constant throughout, the collector current has retained its original value. The time taken, during which the collector current remains constant after the pulse has been switched off, is called the saturation time, TS. From then on, the angle decreases until the cutoff situation is again reached. Simultaneously, the collector current decreases towards zero. Summing up, when the transistor is switched from the cutoff state to the saturation state, and vice versa, 4 steps on the collector current curve can be distinguished. 1, TD, which is the time needed to neutralize the emitter-base junction. 2, TR, the time during which the transistor is operating in the normal state. 3, TS, the time during which the transistor remains in the saturation state. And 4, TF, the period during which the transistor passes through the reverse state to the cutoff state. So to reduce TR, it is sufficient to increase the saturation voltage. But then simultaneously TS will increase, because the amount of holes stored in the base has also increased. In the same way, to reduce TF, the transistor must be brought rapidly to cutoff. But in this case, because the emitter-base barrier region has become wider, the delay time, TD, increases.